Okay. Good evening. Thank you for joining us for the second part of our physics guest speaker series here at SCC. Thanks for and Cass and counselors here. A few program notes before we do introductions. You see a lot of people signing in the back. If you have not signed in yet, but you want to get STEM credit for attending, please make sure you sign in on your way out. Dr. Smith is going to have some time for questions, but if you have a question that comes up in the middle, if you feel like it's a good time to ask, just go ahead and raise your hand and we'll try and address it as soon as we can. So intros. So tonight we have with us Dr. Joshua Smith, who's an associate professor of physics and is also the director of the Gravitational-wave Physics Astronomy Center at California State University, Fullerton. So please join me in welcoming Dr. Smith.
Okay, thank you very much, Phil and Ann. I also wanted to introduce you all to Nusha Afshari, who's an undergraduate student who's working in our center. We were just talking on the way here about how I'm going to give you the kind of unofficial approved version of what it is like to do research in our center, but Nusha can give you the real answers, so please feel free to direct any questions you have to her. Great, thanks, Nusha. So I wanted to start by asking how many of you had heard the talk earlier this week by my colleague, Professor Lovelace? All right, fair number of you. Thanks, thank you. And then I wanted to ask, how many of you are currently in a major like astronomy or physics, or are interested in getting into a major in that direction? All right. Well, I also noticed that one of my great students, Sarah Wood, is here, so I'm going to point to her too. Maybe she can raise her hand. So Sarah was an undergraduate student, STEM² student, working with me last summer, and so I also want to ask her to entertain any questions about what it might be like doing research in my lab. Okay, great. So thank you all for coming out. I really appreciate it. I'm from Cal State Fullerton, and I'm going to talk to you a little bit about something called LIGO today. It's related to gravitational waves. It'll be less theoretical than Dr. Lovelace's talk, more about experiment. So this picture that I'm showing here is a picture of two black holes that are colliding with each other in space. It's a computer simulation. We can't see black holes this easily because they don't give off light. And what you see coming out from the black holes here in these multi-colors are gravitational waves. They're waves of gravity. And that's what we're trying to measure in our experiments with LIGO. And as Phil mentioned, please ask me any questions if you have them along the way. So this is a slide about our Gravitational Wave Center. Maybe you saw this one or someone similar to that. This is located in Fullerton. We have a large center, 3 professors. We have about 20 students. We have a supercomputer that's located underneath the library in our data center. And we have a laboratory area where we have 4 lab rooms. We conduct experiments there. So I do gravitational wave measurement with the facility called LIGO. Jocelyn Reed, who many of you probably haven't met, she hasn't been out here for a talk, does neutron star astrophysics. And we're going to talk more about what neutron stars are later. And then many of you met Dr. Lovelace, who looks at computer simulations of black holes and what happens when they collide. And that's the group that Nusha works in. So Nusha is one of the people running computer simulations. And Sarah was working with me on gravitational wave measurement. So in outline, what are gravitational waves? What are their astrophysical sources? How can we detect them? And what is the status? What is the future? And how could you get involved if you were interested? So Albert Einstein in 1905 discovered an essential law of the universe. And this was in his theory of special relativity. And one of the key tenets there is that no information can be transmitted faster than the speed of light. There's this Monty Python song about the universe, and it says the speed of light is the fastest speed there is. No speed is faster, no information can travel faster than that. In metric units, it's 3 times 10 to the 8 meters per second. Or you could say 186,000 miles per second. So if you turn on a light switch here, every second the light covers 186,000 miles. And the light in terms of radio waves and things like that we've given off from our television has had time to reach nearby star systems and we may be communicating with other civilizations if they exist through light. In 1915, 10 years later, he didn't actually age that much in the 10 years. The theory of general relativity was Einstein's next discovery. This is Einstein's theory of gravity. And you need a theory of gravity if you're Einstein, because the first theory, special relativity, said that no information could travel faster than the speed of light. Newton's universal law of gravitation said that there would be a force between, say, the sun and the earth, and that force would just depend on the two masses, the mass of the sun and the mass of the earth, and the distance between them. But this force was something called action at a distance, like an instant force that was always there. And Einstein said that couldn't be the case. If you moved the sun or made it disappear, it would take time for the information to travel from the sun out to the earth, so the earth would know to go off in a straight line rather than to continue in its orbit. And so Einstein developed something called the theory of general relativity, which said that gravity is actually an effect of the curvature of space-time. I'll talk about that in a second. And that in the situation where the sun disappears, for example, information would have to propagate out from the sun that's gone to tell the Earth to change its orbit, and that propagation would be gravitational waves. So it makes some strange predictions. John Wheeler coined this phrase that's matter, like the sun, tells the space-time how to curve. So if you imagine a rubber sheet, probably a lot of you have seen this demo, you take a rubber sheet, you put a bowling ball on it, that's the sun. The bowling ball tells the space-time, space and time, like a four-dimensional space, how to curve. And space-time tells the matter how to move. So if you take that ball and you toss in a marble to represent Mars or Venus or Mercury, the marble will go around the big mass that's representing the sun. Okay, that's a lot of words for this demonstration. Maybe not making too much sense, but maybe some of you have seen this. So this is Larry Kawano in Idlewild, California at AstroCamp demonstrating curved space-time using a rubber sheet and 3 marbles that could represent the planets. How many of you have any of you been to AstroCamp? Okay, yeah, awesome. So AstroCamp is this camp that's designed for, which grade was that? 6th graders. I think it's 6th and 7th graders. They go to this camp for a few days and they learn all about astronomy from people that have done astronomy. I was actually a speaker there. That's how I recorded this. And so it's a great opportunity. Great opportunity for folks. They have this beautiful spot up in Idlewild where the skies are clear and they have telescopes and they have a lot of great demos in the planetarium. So when the planets begin going around here, they all start kind of far away and they're going around in their orbits. But by the end, they all come down and crash into the sun. Why do they end up crashing into the sun? What causes them to end up in the center there? Friction. And so with friction, the friction of the mat, as the balls are going around, the collisions with the air makes friction. Friction is a way to lose energy. The energy that the balls have in their motion gets lost to friction, and they get closer and closer to the sun and eventually burn up. We're lucky that our solar system doesn't have a lot of friction, so our planets can continue going around in their orbits happily for millions of years. All right, so that's a prediction of what our solar system looks like in terms of curved space-time and how the curvature allows the planets to go around in their orbits. If you take the mass of the sun and keep compressing it into something smaller and smaller and smaller, eventually you might get something called a black hole. Dr. Lovelace probably told some of you all about black holes because that's his most favorite thing in the universe. I think they're okay, kind of okay, so I'll tell you a little bit about them. Gravity's so strong in a black hole that nothing can escape, not even light. So you can imagine a black hole has something like a horizon. This horizon isn't visible like this green ball here, it's actually invisible, and you wouldn't know if you crossed it if the black hole were big enough. You could imagine taking a slice through the horizon and then looking at it, and mapping how strong gravity is by how much the space-time is curved in this picture. So in the areas out here, where there's not very much curvature, where it's kind of flat, the gravity is weak. So curvature is kind of like the slope here. So the slope out here is kind of weak. And as we go in, the slope increases and increases until the slope is about like this down here in the black hole. And that means there's very strong gravity. If you were to, I guess we'll use Nusha in this case since she's here. If you were to take Nusha and throw her into a black hole, she would accelerate because of the strong gravity, and she'd reach about right here. You might, bad things would happen to her. So her feet would be pulled by the much stronger gravity that is closer to the black hole than her head, and she'd get lengthened out into spaghetti, called spaghettification. And if she went through this horizon, she could never come back out. So she would be lost inside the black hole. And that's true even for light, which is the most escapable thing. Light can escape almost anything, but not a black hole. And these are formed when massive stars die, and the pressure can no longer hold up all the mass in a star, and the star collapses down, it shrinks down to something very small. This is a simulation that Dr. Lovelace's group has done, about what happens when two black holes are in orbit. And they do actually end up coming close to each other, like the marbles and the sun that Larry Kawano showed us. These two black holes are orbiting around each other. The black holes' horizons are shown with a black curve, and they eventually merge and form one black hole. So I'm going to play that again. So these black holes do get closer to each other over time, unlike in our solar system. In this case, they're not losing energy to friction. They're losing energy to something else. Down here, there's a plot of a wave. This is a measurement from someone far out, like someone sitting far away like you guys are, of how much stretching and squeezing you might feel from gravity. And this is a gravitational wave, and what's causing the two black holes to get closer to each other is energy that's getting output from the system into gravitational waves. So, gravitational waves are another prediction of Einstein's theory of general relativity. They can be caused when two masses, like two black holes, rotate around each other, and they carry energy away from the system, which can cause the orbit of the system to shrink. Let me just give you a couple facts about them. So there are ripples in space-time, like I've drawn in the picture here, that travel at the speed of light. They were predicted about 100 years ago. In 1915, the theory of general relativity came out, 100 years ago, but in 1916, Einstein fixed an error that he had originally in the calculation and correctly predicted the gravitational waves. They're generated when things orbit around each other. Like if I'm moving my hand now, I actually make some very, very weak gravitational waves. And they interact very weakly, so that means that they can pass right through things. They pass right through us, they can pass right through the Earth, they can pass right through almost the whole universe. And that also makes them hard to detect. And finally, these are a new way to look at the universe. So throughout history in astronomy, almost everything that we've learned about the universe, about stars, about other galaxies, about the age of the universe, we've learned from light that we detect with telescopes, with our eyes. This is not light. This is something, not a different part of the light spectrum, like radio waves or X-rays or visible light. This is a completely different form of communication that we can learn about the universe with. So at this point, this is all sounding pretty far out. How do we know that these things actually exist? Can you trust me at all with any of this stuff? Why are we even looking for this? Well, two folks up here to the right, their last names are Fullerton and Taylor, and they used this very large observatory here, which it's a little bit cut off there, but it's called Arecibo, to observe radio waves coming from two neutron stars. So visible light is just one part of the electromagnetic spectrum, and using these big observatories, we can observe things like radio waves. Fullerton and Taylor studied a binary system, so that's two stars in orbit around each other, of neutron stars, using data from this observatory. So what is a neutron star? This is the area that Dr. Jocelyn Reed studies. A neutron star is what happens when a star dies when it's not massive enough to become a black hole, but it's too large to become something like a white dwarf or a red giant or something like that. So a neutron star is dense, hot ash left over from a star's death. It usually has about 1 to 2 times the mass of the sun, and it has only 10 to 15 kilometers in radius. So this is taking something that's more massive, up to 2 times its mass to the mass of the sun, and having it only stretch from Fullerton to Orange. So they're extremely dense. They have extreme amounts of mass. They can also do some crazy things. They rotate up to 700 times per second. And the matter is above nuclear density. What I mean by that is, in the center of an atom is a nucleus that has protons and neutrons. And that is a very dense object. Just the nucleus itself is very tightly packed. These stars have even more tightly packed neutrons in their matter. Okay, so this slide is courtesy of Jocelyn Reed, and you'll have to defer any very difficult questions to her. This is a movie of what the binary star that Hulson-Taylor looked at might have looked like. It's about 2 1.4 solar mass neutron stars. They orbit each other once every 8 hours. I sped that up so we wouldn't have to stay here until whenever. And what's amazing about the precision of this measurement is the orbit gets only 80 microseconds. A micro is 10 to the minus 6, or like 0.000000. 80 microseconds shorter per year. So they watched this over about 30 years, and they were able to see the very slight change in the orbits as these stars eventually get closer to each other. The stars are going to collide 300 million years from now. And if we had a gravitational wave detector like the kind I'm going to talk about, we could see it. So what you'll notice here, these 2 stars, one of them has these pulses that come out. Those are radio waves, and the thing is orbiting, is rotating, and it has these radio waves coming out, and it acts a little bit like a lighthouse. With our big dish, we detect these waves as little flashes. When they were originally discovered, people thought they might be aliens and called them little green men, but now we know that these binary neutron stars are pulsars. So back to how do we know gravitational waves exist? Hulson-Taylor measured these for about 30 years. They found that the orbit is slowly shrinking. And this agrees precisely with the energy that Einstein said would be in gravitational waves. And they won the 1993 Nobel Prize. All right, any questions so far? I see people getting gradually more sleepy. All right, try to liven things up a bit. Astrophysical sources, what makes gravitational waves? So on this slide, I have a picture of what the sources are, and I have a picture of what the wave would look like when we detected it on Earth. And I also have a sound for each of them. I don't think they're playing yet. All right, so let's see if it works. So the first is, what happens if you have 2 stars that are going around each other and they collide? Hopefully this works. So the orbit shrinks. As the orbit shrinks, they go faster and faster, and it makes a sound like this. All right, so something like that. It's called a chirp. The frequency increases with time. Now, what happens if you have something that has that's spinning and has a little mountain on it, and it just spins at the same frequency the whole time? You get something that sounds like a constant tone. And if you have something that blows up, and we detect it here on Earth, you're going to get just a little bit of energy that we detect on Earth from this faraway thing like a star blowing up in a supernova, and that'll sound like this. It's really just a crack. And then finally, from the early universe, there were lots of things in motion, and there was lots of energy, and we think that there's a sort of random noise because of all these things moving that we can detect with a very sensitive detector, and that would sound like this. So just like static. So we can see the waveforms, we can hear what they would sound like, and that helps us identify what sources they come from. So where might some of these sources live? This is a picture, yes?
When you say mountain, I'm guessing it's like Mount Everest and everything. So what does that kind of refer to?
Okay, great. Yeah, so I'm really glad you asked that question because it's nothing like Mount Everest. So neutron stars are really dense. They are about 15 kilometers in width, and they have about the mass of the sun. We've been trying to measure mountains on them using this approach, and we haven't measured any, but we've been able to set limits on how big mountains could be. And the limit is, for something about the size of 10 kilometers, about a millimeter. The mountains have to be smaller than a millimeter. So when I show a picture of a star that has a mountain on it like this, the mountain's grossly exaggerated. We're actually looking for asymmetries as small as a millimeter on these stars. So it's really incredible how tiny they are, and we haven't seen them. So that's something that Dr. Reed looks into. What kind of mountains could you have on something as dense as a neutron star? And what kind of crust could you have to support those? And the mountains are not very impressive. Go through those. All right. So if you were looking for some of these objects, not using gravitational waves, but just using a telescope at night, where might you see some of these types of gravitational wave emitters? In the Magellanic Clouds in the southern hemisphere, there's a supernova 1987A, which looks very beautiful. This is a picture from Hubble. And so this was one of those pops that you might have heard. And if we had detectors that were running with the sensitivity we have now in 1987, we probably would have heard this and made a detection, the first gravitational detection. There's also a Crab pulsar in the Crab nebulous in the Taurus constellation. So this is one of the constellations in the zodiac that you can see. And there's a pulsar inside of there that's spinning, and probably this would be a good place to look for gravitational waves, and we've tried and we've set limits, but we haven't found any yet. But it's very beautiful, invisible, and in other like radio and X-rays. There's also Betelgeuse, which is the shoulder of the constellation Orion. You see Orion in the wintertime, and this is a star that isn't giving off gravitational waves right now, but we think it's a star that could explode in a supernova sometime relatively soon. And it's only 642 light years away. When I say relatively soon, that's like thousands, tens of thousands of years. And then finally, I hope you know this, Andrea Ghez, who's here in Southern California at UCLA, and her group and a lot of other scientists in the world have been studying a supermassive black hole that has 4 million times the mass of our sun that lives right in the center of our galaxy. And we see other stars orbiting around something that gives off no light and something that has 4 million times the mass of the sun, and we're pretty sure that it must be a black hole. So that's very exciting for our galaxy, and it's also a source of gravitational waves. All right. So I think I'm going to... So if we were to detect gravitational waves, what are some of the things that could answer? Why would we want to do that? Well, it could tell us whether general relativity is the correct theory of gravity. We use general relativity for things like GPS. Clocks tick at different speeds when they're close to the Earth or when they're up in orbit. And so this is a very useful theory, and we'd like to check if it's right in all the different scenarios, all the different conditions. We could find black holes and tell how many there are. We could learn about the structure of neutron stars and what kind of mountains they can support and their kind of internal structure. And we could learn about what happens when stars blow up. So those are some of the things we hope to learn. All right, so that was about the astrophysical sources of gravitational waves. And now I want to talk about the part that I do, gravitational wave detectors. So are gravitational waves detectable? These sound like very crazy things. They're given off by very far away objects. Can we detect them at all? Einstein didn't think so. He said that the effects are so small that it's doubtful they will ever be measured. So I want to look at why Einstein would say such a thing. what effect gravitational waves have? I said that they're ripples in space-time, but what does that really mean? What it means is if you put a number of particles, you just imagine that these are little masses, or so that they don't attract each other, you could just imagine that they're little massless spacers out in space. So just imagine a ring of particles out in space in a circle. If a gravitational wave from two stars orbiting at the back of the room were to come into the page here, at the front of the room, they would do this. They would stretch the distances along one direction, like stretch, and at the same time squeeze distances along the other direction. So they make very small changes in distances that are fractionally extremely small. So the width that I'm showing you, the changes that I'm showing you in this video, are 10 to the minus 1, which is 0.1. You get about 10% change in the distance between the objects. Einstein realized that the gravitational waves that we would receive here on Earth from any kind of object you could think of in the lab or out in space would be very, very small. And now we know how small. It would be about 0.0 and then 21 zeros and then a 1%. So it would be so much smaller than what you see in this video that you could never detect it sitting out there in the audience. You'd need a really, really much more sensitive device than a video like this to find gravitational waves, because they're so tiny. Even when two black holes collide with each other in a relatively nearby galaxy, it's still exceedingly tiny here on Earth. All right, any questions about that? All right. So how is it that we're able to measure these? For this, I want to talk a little bit about optics and waves. So if you have a wave, like a sine wave, and you add it to another sine wave, this is how light adds. Light obeys something called the principle of superposition. So it's basically adding together two sine waves. If you take wave 1 and wave 2, and you line them up so that their peaks are both in the same spot, we refer to that usually as that they're in phase. Their phase is both the same. Then the way to figure out what the wave that will result from adding two waves together that are both lined up is just to add them at every point. So if you add here, you'll get 0. And if you add here, you'll get, let's say this is amplitude 1 and this is amplitude 1, you get amplitude 2. So if the two waves are lined up, then the resulting wave of those two waves is twice as big. And we call this constructive interference. If, however, you slide one of the waves so that its peak, instead of being here, is over here and it lines up with the kind of anti-peak, you call it like a trough from the sine wave, then when you add them together, you get +1 and -1 is 0, you get -1 and +1 is 0, and you get 0 all the way across. And so light has a property that if you line it up just right, it will interfere and you won't see any light in a region of space where two light beams are out of phase. That's what you see here. And so it turns out, you might be able to see this here, that if you have an instrument that has light going along one direction and light coming in from another direction, you can use this property to make very accurate measurements based on how much light you get. Whether you get a lot of light or a little bit of light, that makes measurements much smaller than the wavelength of the sine. And you can see a video like this on Wikipedia of what happens as you slide two sine waves past each other to the resulting wave. I wasn't sure if I would show that because I found it even more confusing than what I just said. But it's a cool video. Why is that important? Well, because what Einstein didn't have in mind when he said that gravitational waves were not detectable is all the technological advances that we've made in the areas of lasers and precision metrology, being able to measure things very accurately. This device here is called a Michelson interferometer. So we use light, which actually, if you zoomed in, would have little waves like I showed. And we shine light in one direction, then in another direction, and half the light goes this way, and this is a device that reflects half the light and transmits half the light called the beam splitter. So half the light goes this way, then the light recombines, and when it recombines, you get this trough or peak measurement, and that allows you to get very, good sensitivity for the situation where you did something like move one of these. If you move one of these mirrors, that has the same effect as sliding the waves, which gives you, at this point here where you're measuring the interference of the two waves, it gives you some light or no light. So we use this to measure gravitational waves by holding the two arms so that the light cancels out, so that you have a peak and an anti-peak, and you get 0 most of the time. And then we wait for one of those gravitational waves to come from the back of the room. That will come in and stretch one arm and squeeze the other. And when that happens, we get a very little amount of light, which corresponds to this very little light. Does that make sense? And it's very fast, yeah.
Yeah, and the gravitational wave is just there. We're not creating it or setting it by anything. It's just, we're assuming it's there.
That's a great question. So, is the gravitational wave something that we create, or is it something that's just there? So the ones we're looking for are ones that nature creates. But we would love to be able to create them ourselves. In fact, DARPA, the United States Defense, I don't know what DARPA actually stands for, black helicopters, secret things I can't talk about. They have a grant proposal out there for anyone who can create gravitational waves and measure them, because it would be like an unjammable phone. The problem is, if you look at what you need to create gravitational waves that you can measure, you can take the strongest materials in the world and rotate them so fast that they reach their breaking strength and break apart, and it still wouldn't be enough gravitational wave amplitude to measure it with our detectors. So we have to rely on things like black holes slamming into each other out in space to generate the kind of gravitational waves that we could see. And that's why in the talk, most of the time I'm going to be imagining some faraway source making them, because we don't know how to generate them strong enough on Earth yet. But that's a really great question. Okay, so some faraway source makes waves, it stretches and squeezes these things, and we get a little bit of light coming out. I think I'm going to skip the next two slides. They're just ways that this experiment is made more sensitive. All right. So now I want to say what limits the sensitivity of this type of a measurement. So we've built some of these things. They're called LIGO. I'll tell you what that acronym stands for in a second. And this is a diagram. It's a little more complicated than the one I just showed. It's shown from an angle, but it's basically laser coming in and the two mirrors. And so what limits the sensitivity? So the three main things are that seismic motion, so motion of the ground, shakes the mirrors. And because they're shaking all the time, we can't see the gravitational waves where the ground is moving. It swamps our signal. Also, the mirrors themselves are made of molecules. And molecules that are moving, molecules that have any temperature have a certain amount of motion associated with them. Temperature is related to the motion of the molecules. The higher the temperature, the more they move. And even if we cool down our mirrors, the molecules in there that are moving still set a limit to how accurately we can measure lengths. Oops, skip that one. And then finally, when we measure light, light isn't entirely accurately depicted by showing these waves. Light is also made up of photons, little packets. It acts both as a particle and a wave. And if you think of it like a particle, it's a little bit like rain falling on your roof. It's very difficult to make an exact measurement of exactly how much rain is falling when the rain is falling in a pitter-patter on a tin roof. So photons of the light that arrive at our detector when we're looking for very small amounts of light, they arrive in a pitter-patter too, and that makes a sort of noise for our measurement. But when you put this all together, I'm going to skip this for a second, you need to do a lot of things to make the detector more sensitive. When you put this all together, you end up having to have the mirrors suspended as pendulums. So just like a suspension in your car, this has some vibration isolation. You have passive and active ground motion. So we have seismometers that measure how much the ground is moving, and then they push using hydraulics and other things to make our mirrors move oppositely, so in the end they're not moving, to cancel the vibrations. And all of this is inside giant vacuum systems. And you have people who are sitting away from those vacuum systems in a control room that are making sure that everything is set up and locked and controlled. and there's control of electronic and servo control and digital control of almost everything you can think of. The temperature, the lengths, the alignment of the mirrors, the power of the laser beam, all has to be controlled. And when you put this all together, you get something like this. So this is the LIGO Livingston Observatory in Livingston, Louisiana. It has arms that are 4 kilometers long. Inside this arm is a vacuum chamber with no air, where just the laser beam shines through. In the central building, just to get a scale, these are cars, so this is a really big facility. In the central building we have lasers, we have the beam splitter, we have a lot of the sensitive electronic in the rooms where people control the instruments. So, Sarah, you visited LIGO Livingston or LIGO Hanford? Sarah visited this facility, which is in Hanford, Washington. It was a beautiful trip for her because she got to visit one of our country's nuclear waste reservations. That's where the land was cheap to build this instrument. And so this is the Hanford version of that. The reason we have 2 is because if we want to measure a gravitational wave from space with detectors that are sitting on the ground, and we know that when the ground shakes, it messes up our signal, and when other things happen, you know, people are nearby and they're doing things that can mess up our signal, it's much easier to make a detection if you have 2, so you can make sure you got the same signal in both detectors. So we check against 2 detectors, and we also check that we get something that agrees with what we think we might get from these astrophysical signals. And we don't only have 2. There's one in Hanford, Washington, and one in Livingston, Louisiana. But we partner with groups in Germany. So I spent 6 years here for my PhD, and also in Italy, there are detectors. So in 2010, we were using these detectors to try to make measurements, and we've spent several years doing that, and so far, no detections. But since 2010, we've been upgrading these instruments, and I'll tell you just a little bit about that. All right, I'm going to talk about status, the future, and you. Yes?
How rare are these waves? Like, do you just sit and wait and hope for a wave to come, or?
Okay, so that's a really good question. Gravitational waves are not rare. They're coming through the Earth right now. They're happening all the time. If I just do this, it makes gravitational waves. But gravitational waves of the size that we can detect are very rare. So for that reason, we run the instruments for years. We ran the initial LIGO instruments that I just showed for about 5 years, and we didn't detect anything. And now we're in an upgrade phase where we're trying to make the detectors 10 times more sensitive, and we expect that we will have a rate of about 40 gravitational waves per year with that new instrument. So it depends on how sensitive you are. It's a little bit like how good your microphone is, what you can hear. And we've just made our microphone a lot better, and we hope it's going to be about 40 per year real soon. So it's actually very exciting. So status, the future, and you. Here's the status of the observations. In 2005, 2006, 2007, 2010, we made about 5 years of observations. We are right here, and later on this month, I'm going to go back to LIGO Hanford for a dedication of Advanced LIGO, the new instruments, and we're going to those are turned on now, but we're going to turn them to start observing for about a year, for about 3 months at the end of this year. And that's going to be the first observations with this new instrument. So why is this hard? Well, binary black hole systems or binary neutron systems make these waves, but even though we've made exquisitely sensitive detectors that are shielded from the outside, the waves that we see are still tiny when we try to measure them. So we have to tease these waves out of the noise. How often do things like these happen? That also goes to your question. There's a lot of information up here, but what I want to say is, how often do these stars merge with each other? How often do 2 black holes crash into each other? We think that happens about 100 times per Milky Way equivalent galaxy, which is an awesome unit. That means in a galaxy like ours, it happens about 100 times per million years. So not very often. If you waited a million years, this would happen 100 times in our galaxy. So our detectors have to be good enough to see many galaxies. All right, I'm going to skip this because I want to have a little more time for you guys. So we have to reach out and see many galaxies in order to get any kind of good rate of gravitational waves. So the way to do that is to improve the sensitivity of our instruments. And the way I like to think about this is keeping our job is analogous to trying to keep crowded and very loud party quiet. We have these big instruments and lots of things can make noise that stop us from being able to detect gravitational waves. We try to make all the people in the party, or all of the things that can make noise in our instrument, more quiet so we can more easily hear the gravitational waves. And the quieter we can make everybody, the better we can hear this music of space. So scientists right now, if you're wondering why is there a gap between 2010 and 2015, scientists right now are working on the instruments to upgrade the technology in them. Nearly everything is being upgraded. So here are some scientists in bunny suits, we call them. These are clean room apparel. You wear clean gloves and clean outfits and get inside the vacuum chambers and put in this hardware. This is actually a mirror here, one of the mirrors for LIGO, and this is one of its big suspensions, which helps to reduce the seismic motion. Here's a picture of some of the other suspensions inside vacuum chamber when they're all set up. And if you turned on the laser beam, the beams would be coming all through here and bouncing off the mirrors to help make these measurements. So to reduce mirror motion, rather than suspending with a simple pendulum, we're suspending by multiple pendulums. So the technology has increased quite a bit there. We're also suspending the mirrors on the bottom by some very high quality glass and using larger mirrors so we can have larger beams which do a better job of averaging out those thermal fluctuations of the molecules that I was talking about. And finally, and I'll just mention this because I think it's pretty cool, we're using some quantum physics, something called squeezed light, which can go beyond the standard limit for how well light can do by using quantum entanglement, by using quantum properties to get a better sensitivity for the detector. And I just pointed to a paper here in Nature Physics. So what is the status of this big upgrade as of today? From 2010 to 2015, we've been working on this. Currently, both of the advanced LIGO detectors are more sensitive than they were in 2010. To put this into perspective, in 2010, the sensitivity was 30 to 40 megaparsecs, which is millions of parsecs, which that's an astronomy term. It's similar to light years. So now, compared to 40, we have 130 and 80 for Livingston and Hanford, and those numbers are just going to grow. And what that means is that we get to see more and more galaxies. I'll show that in a second. So with initial LIGO, we could, in this picture here, all of these little white dots are galaxies that we could see, or that we could listen for these in-spiraling binary neutron stars. With initial LIGO, we could see and hear an area like this. And now with advanced LIGO, we have 10 times the range, which is 1,000 times the volume of the universe that we think we can see. And this means that we have a distance which is increased by a factor of 10, but a rate that used to be 1 out of every 50 years. We thought we might get one with initial LIGO. We didn't find any. Now we think we're going to have a rate of detections of about 40 per year. So it's a really exciting time to be in this field because these enormous, very sensitive detectors are now good enough to make detections. Okay, so let me check. So it looks like we have about 10 minutes before the end, but I want to leave time for questions. So let me just finish about the science by saying that many binary systems, like the Hulse-Taylor binary, have been observed to be shrinking due to gravitational waves. So that's how we know that these waves exist. Earlier this year and last year at the news, there was a discovery that came out of polarization in the cosmic microwave background that's associated, people thought, with gravitational waves. There's been a follow-up of this, and there's still research happening, but people think that that signal might have been related to dust. And I think this is exciting because it's showing how kind of fluid and dynamic science is and how it's happening right in front of our eyes. Advanced LIGO, the instrument that I told you about today, and other instruments like pulsar timing are going to be capable of making detections in 2016 and thereafter. And in the future, when I'm very old, there will be space-based missions that are similar to the ones that we have here, but don't have the seismic effects from the ground shaking like you do on the Earth. All right, so that's the science, and I want to switch gears just for a couple of minutes before giving Nusha and Sarah and myself some time to answer your questions. So I wanted to point out that we have this center at Cal State Fullerton, and this is a picture, shameless plug by using a picture of Kip Thorne, who was giving a talk at our center about black holes and gravitational waves and what science is going to be done at Cal State Fullerton. And for those of you who don't know who Kip Thorne is, besides being a renowned physicist and professor at Caltech, he's an emeritus professor now, he's also a producer of Interstellar. And I think one of the scientific creative minds behind the movie Interstellar. So if you've seen Interstellar, Kip Thorne also wrote the book The Science of Interstellar. And so he's a very big name in both Hollywood and in physics. This is a picture of some of our students. Is Nusha in this one? Yes, there's Nusha. And Sarah's not that one. This is some of our students in summer 2014, located in the center in Cal State Fullerton. I hope I'll see some of you there someday. And I wanted to just mention a couple of the students that we've had. So we've had a number of transfer students, and that's part of why I'm here today. I hope we'll get more in the future. We've had a number of transfer students who have done great. Fabian McCall was a transfer student from Santa Ana College. He was a researcher for 3 years, and now he's a PhD student at Syracuse University. He led the writing of a paper, and he's been co-author on several other papers, and he had some very nice research opportunities. Some of the CSUF students in my area have had opportunities beyond what you'd get at Fullerton. So Daniel Vanderhyde and Adrian Avia Alvarez, they both traveled to Pisa, Italy, where the Leaning Tower is, and they have a very nice university there. They were located at the university, but they were working at the Virgo gravitational-wave detector. Excuse me. Gabriela Serna visited Kitney in Tucson, Arizona. Cynthia Padilla maybe took the most extravagant trip. She was a summer researcher in Seoul, South Korea, a couple of years ago. So, if you were to join my group at Fullerton, what kind of opportunities would you have for research? So we measure some of the light properties of the mirrors in LIGO. We also characterize the detectors and try to find and eliminate noise sources, like making this party quieter. We develop software to view the LIGO data, and we also do some telescope image analysis associated with gravitational wave trends. All right, so thank you. And are there any questions for me or Nusha or Sarah? Yes?
Can you just define what LIGO is? LIGO?
Oh gosh, I'm sorry, I never did that. LIGO is the Laser Interferometer Gravitational Wave Observatory. It's a mouthful. So laser interferometer is the big L-shaped thing with the red lines. And then the Gravitational Wave Observatory just refers to it being kind of like a telescope to see gravitational waves. Yes?
Could you say that one more time, because that was actually a mouthful.
So it's the Laser Interferometer Gravitational Wave Observatory.
That's what I'm talking about.
Right. Yes?
So when the gravitational waves are created, do they expand outward on one plane, or is it like an expanding sphere?
It's more like an expanding sphere, but it doesn't always have to have the same strength in every direction. So if you have two stars going around each other like this, the gravitational waves will expand out in a sphere, but they'll be stronger in some direction than they are in the other direction, but it expands out in the speed of light in a sphere. Nusha and I don't know if Sarah, if you'd like to come up too, would you guys want to come up and there maybe hopefully you guys can get some questions too? All right. Yes.
Is there a limit to where they would stop? Have we considered that? Or are we assuming the universe is infinite?
So that's I don't think there's a, gravitational waves interact very weakly, and I don't think there's a limit, like they don't hit a wall. And we think the universe is finite, but essentially there's not, there's a limit in how far away we can see that, because there's a limit in the time that the universe has had for light to propagate, or for gravitational waves to propagate, but that's really the only limit. It's like the age of the universe times speed of light.
Also, what are the prerequisites for the research program?
For the prerequisites for the STEM² research program. I'm not sure if I know that as well. Do you have?
Yeah, I could just say, just very quickly, for students in the STEM² program, we're coming into the 4th summer of research. 13 students were already chosen for these wonderful spots over in Fullerton. We have one more year of summer research coming up in the summer of 2016. Essentially, to be eligible, you have to be a member of the STEM² program. You have to be meeting with a counselor once per semester, and myself or anybody here on campus. And you have to take part in 2 STEM-related activities. You keep up with your STEM² requirements, and we start recruiting for these summer research experiences probably at the beginning of the year. So we'll be looking for information in January or so. Please apply.
Yes.
I understand that it's very exciting for like LIGO to like turn on again, I guess, and capture this wave. So we're expecting 40 a year. With the information that they get from LIGO, what's the next step after like getting the information?
So the first step is to directly measure the gravitational waves, which we've never done before. But then the next step after that is to try to do some astronomy with the instrument. So it's a new type of, gravitational waves are a new type of way to look at the universe, and we're hoping that there'll be things there that we haven't thought of, like the unknown. And we hope to use it as an observatory to learn things like where black holes are, how many there are, things about neutron stars, and start to, like you would use a telescope, start to learn about things that you didn't know before. Now, in developing these instruments, there has been a lot of development of technology in order to push the limits of sensitivity, push the limits of optics and things like that. And those, of course, kind of feed back to industry and help push laser technology and mirrors and things. And that's related, but not the mission, but it's also a positive kind of spin-off.
So basically like LIGO serves like as a telescope for what we can't see.
Yeah, I think that's a good way to think about it. Yeah. Yes?
So you kind of touched on it during the lecture, but what are some of the like practical applications of all this? Like what can we do with it next after we start researching it and our research becomes more starts to pay off more? Like you mentioned how it can kind of affect how we use like telecommunications and stuff like that.
Right. Yeah, so I touched on that in a couple of places. Right now, gravitational waves are not a practical application because we have the best detectors we've ever made, and they're not at the moment good enough to detect gravitational waves coming from these huge, massive collisions of black holes and things. But as we continue to push the technology, I think we're seeing, I didn't really mention it, but there are other technologies besides LIGO that are being developed to measure these, and where people are becoming innovative, and we're starting to see different possibilities come out of that. And so I think one thing is the technology for measuring the waves is going to increase. Now, I mentioned something like a DARPA phone. If you really push that many, many years into the future, what we have now, maybe you could get a type of communication that you could communicate over vast distances with and be able to detect down the other end, and something that couldn't be jammed because it can pass right through planets and things like that. But that's like not a very practical application because it's so far in the future. And then I would say the most practical thing is that in the research that we're doing, and including the supercomputer research that these guys have been doing and the optics research that we're doing, we're pushing the envelope on current technology and trying to make that technology just a little bit better, which helps in lots of areas. So if I help make a mirror better, that may help telescope manufacturers, or that may help some other experimenters do a little bit better in their area, and likewise for me. Yeah.
I think I may be oversimplifying this, but to increase the sensitivity, could you send LIGO out to space? And then, or that costs like too much to send that thing over?
Yeah, no, we absolutely would love to send LIGO into space, and there's a program, if you want to Google it, called LISA. So here's a little picture of an artist's conception of what something like that could look like. So you have an interferometer that's very similar to the type that we were discussing. You send it into space, and then you don't have the seismic fluctuations. You don't have some of the nearby roads and traffic and people talking, and so in principle you can make the arms as long as you want, which gives you better sensitivity. And so this is a really nice idea, but sending things to space is very expensive. And also there's a long timeline, because on Earth we can work on things. In space you have to send it up and it has to work, it has to be perfect. So you have to have a lot of planning to make that happen. And so that's why I think the timeline for something like that is longer, like 15 years in the future.
Continue.
All right. Yes?
You mentioned using the like a telescope in order to see what black holes are. But because they're so rare, and is it like is it a pulse, or is it more of a traditional wave that it gives off? Can you actually use that for that?
So, Nusha, you look at binary black hole waveforms. You want to talk? You want to say something about what they might look like when we detect them?
From what I understand from research is that, you know the waves we saw? Okay, so you know the waves we saw where it made that sound, whoop, that wave? I think if you have a slide of it where it's literally in the noise of the universe. So in all that static, we're going to have this small little window of finding a chirp. That's what I understood from it.
And that signal will last just as long as the sound you make, because that sound is pretty much the signal.
Yeah, it's like this tiny, tiny little window. So can you imagine like finding 48 years?
So the analogy to that is telescopes we don't always use telescopes to look at a star that's always there. Sometimes I'm sure you guys have seen things like where people have discovered supernovae. You look at a galaxy, and the galaxy looks the same for as long as we've ever seen it, but all of a sudden there's a new bright star, it looks like, and then that kind of fades away. So the universe is transient, it changes, and sometimes you get a new star appearing. It's very similar to sometimes you would hear a pop from a supernova, or sometimes you'd hear two stars going together. But there are signals like these spinning neutron stars with mountains that would be very long-lived, that you could look at for a long time, and that would be more like a star in the sky.
And then we can use that to approximate kind of where it is.
Yes. Yeah, the way we can approximate where things are is by using like triangulation. When the signal arrives at the different detectors, we can use that to point to a spot in the sky.
Yeah, and it's not like here's the Earth and all the waves are coming from this direction. It's like they're coming from all different directions at all the same time, and we have to be able to say, okay, this piece is two black holes coming together, or this piece is two neutron stars coming together.
All right, those are really good questions.
All right. Well, I want to just say again, we've been incredibly fortunate to have the support and the partnership with Cal State Fullerton. So a big round of applause for
Nusha is Sarah.
Sarah Wood, one of our stars. For those of you, so thank you all for coming, and we hope to do more events like this in the coming semester and the coming year, so keep your eyes open for that. If you didn't get a chance to sign in on your way in, please make sure you sign in on your way out, especially if you're in the sub-square program. And thank you for coming.
Thanks everybody.